Hello and welcome to this Intro to Capital Modelling with Python talk on dependencies modelling called Size Matters, the Impact of Granularity on Correlation Strength. I'm Dan Gelderd. I have one slide quickly to set the scene. We are building an internal model and we are selecting correlations to apply between our classes of business. We're going to use a flat correlation structure where all of our classes are represented in one large matrix, but we have got a concept of divisions, larger business divisions, and we're saying that classes within a division have a higher correlation with respect to each other than classes that are in different divisions. And what we are going to look at in this talk is the impact that your choice of class granularity has on the observable correlation stats at the aggregate level, and how that's going to impact the way you need to think about benchmarks and parameter selection at the individual class level. So we'll jump into a demo using the CaPytal framework and have a look at some of these phenomena. So here is a dashboard built using our CaPytal modeling package in Python to help illustrate some of these ideas. So we'll start looking at the parameters for a simple model. We've got a divisional structure, as we said, with a number of classes in each division. And this is going to represent the granularity of the modeling. So we're going to imagine what happens as we start off modeling classes within each division at quite a coarse level of granularity, and then what happens as we split this out to much more fine granularity. We've got the parameters for correlation between classes that are within a common division, and a separate parameter for the correlation between classes that are in different divisions. And just to show what this looks like, we have a sort of intermediate result being shown here for the full padded out matrix. So we can see between Division 1 classes and Division 1 classes, we've got that 20%, but if we go down and look between Division 2 classes and Division 1 classes, it drops to 5%. So these are all perfectly equal to the parameters because this is just the inputs being padded out. We can see what the total loss distribution looks like. Get some aggregate stats here for the total losses. And we can look at the class losses after the correlation has been applied. So this will give us the actual class-to-class correlation that was achieved. So roughly the 20% for the Division 1 classes, dropping to roughly 5% for the cross-division classes. The result I want to look at, though, is what the results, the implied correlations are when you aggregate the classes up into their divisions and then measure the correlation between the divisions. So here we just have a correlation matrix between the divisions at a total level, and we see a much larger correlation. So whereas it was only 5% as an input between the individual classes across divisions, when you aggregate up to the total division level, that's been amplified up to more like 15, sort of north of 15%. And what happens is we increase the number of classes. So we could increase this to 50 classes in each division. Save these changes. Look back at the resulting division-to-division correlations, and we can see that by increasing the number of classes, this has had an amplifying effect here. And we can explain the phenomenon here with a formula. So we've got a formula here that kind of gives us a prediction of what the answer should be based on sort of just the variance, covariance type formulae. So we'll go into that in a second, but you can see this is predicting we should get something like a 23% correlation between the divisions, and that is what we're seeing. So it's an understandable effect, but just an interesting one, that high degree of class granularity very highly amplifies the input correlation between classes when you aggregate them up into that divisional total. So let's have a look at where that formula and where that result kind of comes from. So we're going to let D1, D2 be two divisions, each have n classes. So we're going to assume this is pretty symmetrical. We're going to talk about the sum, S being the sum of classes within a division. The classes are all going to have a common sigma squared variance, and the correlation between classes is either going to be row W for within a division or row X for cross divisions. And we're going to define the aggregate correlation measure to be that between the two divisions at a total level. And so by definition, this is the covariance over the square root of the product of the variances. And then we can use the fact that covariance is a linear operator. So the covariance of these two sums is the sums of the covariances, which we know from the number of classes and the correlation across classes and the standard deviation of the individual classes. We've got the variance of the sum as well, which we've got from the standard sort of variance covariance formulae. And so we can put these into our correlation formulae and we derive this kind of headline result. And what are the ways to interpret this? Well, we can see we've got n in the numerator and the denominator. But the n in the denominator has got this factor of row W, so the correlation within the divisions. So it's essentially when we've got a small row W, and generally things aren't very highly correlated within the divisions, then this kind of takes out the factor of n on the denominator. We end up with n pretty much purely on the numerator, and we get behavior that's almost proportional in n. So as you increase the number of classes, the aggregate correlation between the divisions is scaling up linearly with that number of classes. So that this between class correlation row X is getting largely scaled up. Whereas when row W is large, when you've got a high degree of correlation within each of the divisions, then the sensitivity to the number of classes is much less pronounced. You've essentially got lots of copies of the same thing rather than lots of different things. So we get this n on the numerator and the denominator, which largely cancel out, and we get behavior that's much more invariant in n. So these formulae kind of work based on linear correlation, but the Spearman's row correlation that we were looking at in the model will be kind of qualitatively the same. And we can use that formula to kind of just look at what the impact of row ag would be, this kind of between division correlation. What is this for different values of n, the number of classes, different values of the between class correlations within the divisions and across the divisions. So we can see that when this correlation within the divisions is very high, so when row W is very high, we've essentially got lots of copies of the same thing. So in this limiting case where it's 100%, then we've essentially just got really one effectively free class per division. And so the behavior, the correlation between classes across divisions is the same as the correlation between the divisions themselves, because it's essentially kind of just collapses to one thing. But as we look at a lower value of row W, so in our example we were looking at 20% and 5%, and we saw that at 23% when you've got 50 classes. With 100 classes goes up even more to nearly 50%. And if you've got very weak correlation within the divisions, then this relatively small value for row X, something like 5%, could magnify up to nearly 50%. If you've got symmetrical correlation, so within the divisions and across the divisions it's the same, when you aggregate up and look at the effect, the correlation across the divisions as a whole, you're getting close to 92%, which is a huge kind of huge output figure. So the takeaway really from this is that what high, medium, and low means when you're thinking about correlation parameters kind of varies depending on the granularity of the modeling you're looking at. We make a lot of use of benchmarks and things like that when we're calibrating and validating the correlation assumptions in capital models. And I don't know how much people are always conscious of the level of granularity as being a big driver of the sort of the aggregate correlation strength. So what you might look at as being a standard strength correlation between two lines of business, if those are actually very granular lines of business and there's lots of them, then when you aggregate those up into your divisional totals, you may now have a much, much stronger correlation effect between the divisions than you were expecting. So what was that benchmark correlation that you were using and applying between the classes? Was it a kind of division to division correlation benchmark, or was it a sort of very granular class to class correlation benchmark? So I think take care when you're selecting and using benchmarks, and make sure that you are comparing at comparable levels of aggregation and granularity. In particular, if you've got a model where some of your divisions, some of your lines are split out into very granular modeling classes, whereas others are much more coarse, then your matrix will have potentially quite a strange shape, and having flat correlations across that matrix may not really make sense, because the more aggregated classes, the more granular classes, really should have a different kind of level of what high, medium, low means. We often pick the granularity of class modeling in our internal models for other kind of operational reasons. We're thinking about the granularity of the business plan. We're thinking about the granularity of the outwards reinsurance attachment. So it's often things like that that dictate the granularity of classes in the model. But when we change that granularity, or when we select that granularity, I think it's important to have some of these kind of phenomena in mind, particularly when you're selecting your dependency structures and your benchmarks, to make sure that they are appropriate for the level of granularity you're modeling at. Let's have a look at some of the code behind this dashboard demo. It's all been built using the CaPytal package, and it's taken about 150 or so lines of code top to bottom. So let's have a quick look through it, and then we'll see if we can take the example one step further. So we're importing from CaPytal a few helpful building blocks. Our variable object, which is the main atomic item of our models, carries all of our data structures and has a lot of helpful functions for operating with other variables. So it's our main kind of building block for any business logic. A few helper functions for simulating values and for applying correlations and measuring correlation stats. There's a very small section where we're configuring the model in terms of setting a sim count, setting a set of statistics we'd like to look at. And then we define the dashboard in terms of this model. Really, we're just giving the model a title and a description. We're listing out some parameters that we'd like to see. These refer to variables within the code that we're about to write for the actual logic. And then we're defining a few variables that we'd like to see, again, just by referencing variable names. You can see here we've got a description, which includes some latex. That's how we got that nice formula to render on one of the screens. We've got some results related to correlation, where again we can refer to variables by name, and we're going to see the correlation stats appear on those tabs. And then below that we see the actual function that we are wrapping as a model, that contains all of our business logic. So this is where we actually express the modeling. So we've just got a simple variable that we're declaring as a literal with 3, initial value of 3 to represent our number of divisions, simple Python list to generate division names, a new variable that just starts initially with a value of 10 for each of the divisions, and that gives us our input for the number of classes per division. Then a little Python list just to work out what the class names are going to be, and a class to division mapping just to help us later. A small variable that we're initiating from a dictionary just to give ourselves some initial parameters for our loss distributions. Then we simulate the class losses using the simulate values helper, passing in those loss parameters. We've got a couple of variables that we're initiating with our initial values for the correlation within divisions and the correlation across divisions. And then we're using dictionary comprehension just to pad that out into a square matrix and converting that into a variable from dictionary. We are applying a Gaussian correlation using those input class correlations to the losses. We're not using any method for approximating to a positive semi-definite, so if it's not a valid input it will fail, but we could have used an alternative method here to go to an approximate nearest neighbour. And then we're adding a dimension back onto our class losses using that division by class mapping we derived above. Then we can sum into the division and we can sum further into the total, and we can measure the correlation stats on the losses by division, and that's how we saw that final table. So all in all, that's about 150 lines of code, and that gives us the dashboard we've just been looking at. We'd now like to take the example a little bit further though, so we're going to see if we can actually do a little bit of model development using the help of Copilot running as an agent using the GPT-5 model. So I'm going to start it off with a prompt. This is something I wrote earlier, but I'll just show you the prompt. So I'm trying to extend my model to allow for a common driver factor like inflation, to see the impact this has on class level and aggregate loss amounts. I'd like a common driver variable with a standard deviation that I control as a model parameter. Normal distribution is fine for this. I want it to have a mean of 1 so it doesn't affect the class means. I'd like to analyse the impact in a number of ways by looking at the impact on the mean, 99.5th and the 99.5th stress. For class level distributions and the total loss distribution, this can be a simple ratio of the stats for the adjusted over the unadjusted amounts. By looking at the achieved correlation between the total and the common driver, and by looking at the achieved class-to-class correlation matrix before and after the common driver. And I'd like to see the new standard deviation parameter on my model dashboard, as well as results tabs for the diagnostics. So we'll grab this prompt and we're going to chuck this in and we'll see how it goes. And we'll watch how it responds. So it's currently just using the current model as a reference, so we can see the context it's making use of from the current repository. Importantly, it's not finding a this is one we built earlier example, so it should just be doing all of this based on the prompt and the sort of natural instructions that it's got already in the repository. So it's a very nice way to run Copilot in agentic mode. It will it sort of empowers Copilot to run scripts, which can include rerunning your test scripts, running your overall model that you've built, checking it for errors. It can then iterate over its own work and try and fix its own bugs and improve the model, try and get you to a working state. It does it in quite a transparent way, so we're going to see the different steps that it is taking as it goes through the modeling. We can click on the changes as they start to come in. We should see inline edits that it's making to our code. We get to choose whether we keep those or reject them. Of course, we're working in version control, so we always have the option of reverting back if we don't like what it's doing. So we'll just give it a minute to see if we can work this out. Here we can see it's searching for a particular function, particular references. It's identifying them in the CaPytal package, so it will inspect the underlying code base when it's running in this way and try and find references, examples, documentation that it can use to improve its accuracy. Great, we see it start to come in with its edits now. We can have a look through these in line. We can see it's added a new parameter to our list of parameters, so we should see something appear there. It's defined new results. Now we'll get into the actual model code. We see it's renamed some things to refer to baseline instead of the initial, so we can record the baseline as well as the adjusted. Inflation driver standard deviation, it's created a variable for us with an initial value of 5%. Creating a variable from a dictionary of parameters with the mean of 1 that we asked for and the input standard deviation. Then it's generating from a normal distribution like we asked for using simulate values. It's applying the inflation driver to the baseline. It's calling our stats method, calculating the ratio of adjusted stats over baseline stats as we asked it to do. It's working out a correlation matrix. I think it doesn't need to do this. This has gone a little bit too deep. It seems to be doing it itself using NumPy, so there really should have been no need for it to use NumPy. So we'll see if we can improve that with an updated prompt. But we'll see how this is going. So now it's finished producing this. It wants to run the model and test it out. So we're going to allow that. This runs a command in the terminal to run this demo model. And we see it's generated something initially that didn't work. So we'll see if we'll give it a chance to improve its work. This wasn't its best effort here, but we'll see what's it done so we can see how it's tried to patch it. So here it's getting stuck in this section where it is trying to work out a correlation result. Now, the CaPytal package has got good correlation calculation stats already available, so it's a shame it hasn't identified those and made better use of them. So we're going to prompt it and see if we can improve that in a minute. But this is where it's got stuck, because it's trying to go a little bit off-piste here and actually deconstruct the variables and make its own way. So we could allow this and let it keep going, but I'm actually going to stop it here. And I'm going to give it a prompt about the lack of need to calculate these correlations directly. The CaPytal package already has good helpers to calculate correlation. And can you please try and use these using NumPy directly? Let's see if that helps it improve its response. So we can see here it's been looking for these correlation functions that we've hinted it towards. It's not done a great job finding them, so perhaps some opportunity for us to go back and improve the indexing of the package and the instructions that we give the agent to help it find certain packages more easily. but it has found the correlation package within CaPytal, so it's reading through there, so maybe it will find what it needs and produce a better response from that. Okay, so we've got our edit, taken 36 lines of numpy out, hopefully, yes, so this function has come out, and putting in instead, brilliant, so it's recognized that there's an additional helper for calculating pairwise correlation stats, so it's done that perhaps, and then presumably making use of that here, so it's got rid of a lot of code that it's done directly. Great, let's allow it to run that and see if that makes a better go of it. Super. So we can see dashboard has come back, and we can have a look at what it's done. The parameters tab still has our existing parameters on from before. We can see we've now got a new parameter at the bottom for inflation driver standard deviation with the initial 5% that it put in. What else is new? We have an inflation impact diagnostics tab, which is new. So let's click on this. Okay, so it's given us class losses, stat ratios. So we see the 3 stats that we asked for and all the different classes. No impact on the mean because we asked for a mean impact of 1. But we can see at the class level we're seeing some 2%, some 1%, some even negative impacts on the 99.5th and even on the 99.5th stress. 3%, but in a couple of places, but quite negligible impact on some classes. There's an odd total here, which maybe we'll try and clean up with a further prompt after this. Looks like it's just appended a total on, which is the sum of the rows above, which we can ask it to try and clean out for us. What else have we got on here? We've got total loss stats. So where are these? The stat ratios for the individual classes. This is for the total. So we can see here we've got a measurable kind of 5% impact on the 99.5th and a much more measurable impact, 11% impact on the 99.5th stress. Again, we've got this total appended here, and it's also calculated the adjusted total, so the total claims versus the driver, what the aggregate correlation is, and that's been estimated at 30% here, so that was another stat we asked it to produce. So that looks good. We have class losses after correlation, achieved class correlations. So this looks new as well. Achieved class correlations before the driver, and below that, achieved class correlations after the driver, so a little bit higher. So we can see slightly higher class-to-class correlations being measured after the driver. So that was something else we asked it to produce. So it seems to have produced all the extra diagnostics we wanted. So let's keep what it's produced and say thank you very much. There are some total rows on the new stats tables that look odd. They seem to be summing the other ratio stats. Can we please remove these? Let's see how it does. So just an additional 2 lines. Great, it's kind of got that right. It has worked out. There's an optional argument you can pass in when you're defining the results you want to see, and it's just telling it to not append subtotals. So that's super. So let's get that running again. Great, so we've got our dashboard back again. Let's have a look at these tables now. Great, so we can see the impact has been to remove the total, so it looks a bit smarter now. So that's probably everything we're going to do on the development side for this dashboard. Let's just see if we can use it to make this point about inflation modelling now. So here we see initially with our 5% inflation standard deviation, we're getting pretty measurable impact on the 99.5th stress at the total level, some impact at the class level, but not really very strongly systemic, some up, some down. So definitely seeing this amplified effect here. Let's just check the model is all actually working and still nice and dynamic. So let's go back and increase this to a 10% correlation, a 10% standard deviation on the inflation driver. Save that, look back at the diagnostics, and we see this much amplified 25% impact now on the aggregate 99.5th stress, whereas at the class level, yes, we are seeing some measurable impact as well, but very much amplified at the total level. So to sum up, we've seen how having lots of small things with loose interaction can have large aggregate impact. We saw that with the class-to-class correlations, where we apply across many small classes, but there's a lot of amplification as we get into the divisional-to-divisional correlations. And we saw that with structural drivers like inflation, where the impact on an individual class can be only marginal, but you can still have large impacts on the aggregate results. So the takeaway is to take care when selecting correlations and when interpreting results across different levels of granularity. That talk was an apt metaphor for actuarial collaborative technology, where we are developing the CaPytal package as a network of loosely connected independent actuaries and developers contributing to the project. If you'd like to know anything more about CaPytal, please email me at danielgelder@collab.dev or check out our website at collab.dev. Please follow me on LinkedIn if you'd like to see more videos like this in the future. Thank you very much for listening.